Okay, hi everyone. So this is a run through for Lab 6. Now we've skipped over 5 because that's just some recap, but this one builds on the context of the last lab because in here we look at the third major distribution that we're interested in. And that distribution is called the T distribution. Now, this is the function that we're going to use here, or the family of functions. And just like the others, so we had a letter that comes before it. So you can see P here, and then the name of the distribution afterwards. So before we had binom for binomial, norm for normal distribution, and here it's just T. So for probability in the T distribution, the function is PT. Now, from here, really, we're going to start using functions like this. So this is t-test. So it's a test that uses the t-distribution to generate some of the outcomes that we're going to look at in this script. So essentially, all of this script is going through stage by stage, manually calculating the sort of outcomes that we get from a t-test. So this is a bit mathsy. We're going to be going through some formulas on this, but ultimately, this is just so we can understand what it is that t-test does. Now, this is still fundamentally pretty similar to the stuff we've done before. So all we're going to be doing is drawing some graphs and looking at the area under curves. But the additional aspect of this is that we're going to be thinking about this in the context of samples. Now, this is something that Chris has talked about in the lectures. So, a sample is ultimately it's the part of the total population that we have drawn a part of, and we want to be able to say, well, from our sample, what can we tell about the total population? The way we do this is by including in our calculations this, the n, the number of observations in the sample. And we'll see in this script how we can incorporate the n into some of the calculations we're already doing in a way that allows us to generalize from the sample through to the population. In this first example, though, we're going to look at how we can do this using a comparison between the sample and a known uh, estimate from the population. Now, usually we wouldn't have this. Right? Most of the time, when we're using samples, we only have data from the sample. But there are some scenarios under which we might have data from the population too. So, for example, if I had a sample that talked about the age, gender, etc., of that sample, I had data for that. I might also have the population mean because we have things like census data, for example, that might allow me to compare the population to the sample. So this is an example of how we would calculate this using this idea that we have both a sample and a mean. Now, what we're also going to do is we're going to compare this to what we call here a number of interest. So if you watched the previous lab, the comparison here is that we had a standard deviation, we had a population mean, and we had our number of interest. And in these previous labs, we looked at the idea of a population mean being a score of 55 on a university exam, the standard deviation being 15, and our number of interest being the number 70. So the score for a first. Now, in this example, though, we're going to plug the following numbers in. So we're going to imagine that we have a sample of 30 cat owners, and we've asked them how heavy their cat is. In this example, we're going to imagine that we know the population mean, so some broader group of cats, is 4 kilograms. And we know that the sample standard deviation that we draw from our hypothetical data is 0.75 kilograms. And what we're going to try and calculate is what the probability that the mean of the sample, so not the mean of the population, is 4.75 kilograms. Now, the way we do this is we move through a series of specific calculations. And the first thing we're going to need is the standard deviation of the sample and the n, so the number of observations. So the number of observations is 30, and the standard deviation is 0.75. So I'm just going to read these into the data here. So we have an n of 30, standard deviation of 0.75. And the first thing we're going to calculate is what we call the standard error. Now, the standard error is what we get when we divide the standard deviation by the n. So 0.75 divided by 30. That's going to give us the standard error. Now again, I'm just going to save that as a value, and you can see that the standard error is 1.3 or so, 0.14 if we round that up. What we then do is standardize the value of interest. So here's our value of interest. It's the 4.75 that we got from here. And our mean, of course, is 4. Now here's the calculation. And you might notice from the previous lab, we did something similar. So we derived a z-score from our value of interest minus the mean divided by, in that case, the standard deviation. So what we've done here then is we've just replaced the standard deviation with the standard error. And this gives us something called the S value. So if I run this, oh, I haven't run the whole thing. Our S value turns out to be 5.4. So there's my S value there. The final thing we do then is we just plug this information into our new function for this week, which is PT, probability given the t distribution. Now there is one more thing we need for this, and that is what we call the degrees of freedom. And we'll talk about this later in the term, exactly what degrees of freedom are. But for the purposes of this, the degrees of freedom just need to be Rn. So Rn is 30. And then we subtract 1 from that number. Now this is because it's a univariate test. So there's only one variable involved here. So we only need to take n and subtract 1 from that. So the values we put into our PT function then are our S value. So writing S.value here is just going to call up this number from over here. And then df for degrees of freedom. And because we've created this as an object, it's going to call up the number 29 from over here. So here's our degrees of freedom. Now the final thing is then, because we are interested in the probability that the sample mean is greater than 4.75, we're going to subtract this value from 1. If we're interested in this value, 4.75 being the less than the mean, or the probability of getting that value as a mean being less than 4.75, then we would delete this. And we would just calculate PT. But we're interested in what's the probability of getting a sample mean of more than 4.75. So let me just undo that. And let's calculate this value. So this is the figure we got. Now this, whenever we see this on the end, e minus some number of figures, this is because this is 3.3 to the minus 6 power. So this number is almost equivalent to 0. What this means then is that the probability that the sample mean is greater than 4.75 is less than 1%. So that might be a little bit difficult to get your head around initially, so let's see what this looks like in graphical form. So firstly, let's look at a normal distribution. So here is our normal distribution. So let's draw a normal curve here. Not the best normal curve. Let me try that again. Now, our mean here then was 4.75. No, sorry, our mean was 4. So 4 kilograms. So the question was, how much of this distribution is contained by possible values more than 4.75? And the answer that we got was that it was a very small amount of this distribution. Now this is probably an overestimate, but essentially what we've calculated is that the area under the curve here equates to a P of basically 0. So almost no values should be more than 4.75 kilograms. Now we might think, what's the point of this calculation? Because surely I could just calculate my real sample mean up here from my sample. But in fact, that's exactly the point. So if, for example, I calculated the mean of my sample, so the mean weight of the cats in my sample, and I did get 4.75, well, that means that it's very unlikely, right, with this p-value of almost 0, that in fact my sample comes from the same population as this one. Now, the example I used in some of the labs this week then was that, imagine that this is age. So if I took the population age for the UK, so the entire population for Britain, and then I took a sample of the classes for data analysis 1. Now, the mean age for data analysis 1 would be much lower. It would probably be something in around maybe 19. Now, there would therefore be a very low probability value that my sample was the same as, sorry, my sample is over here, would be the same as the population. So what I could say is that my sample was statistically different from the population as a whole, because this is what we mean by statistically distinct. So statistical significance is another way of putting this, is just calculating this area under the curve and comparing one number to another number. And this is useful across a broad range of different things. And when we look at t-tests, we'll look at this concept of statistical significance a bit more. Now, the other thing we can, of course, do is that we can do this the other way around. So there we just looked at an example of deriving an area under the curve from a given point. But as we know from the weak on normal distributions, we can also derive points along a curve from the area under it. And this has another use as well. And that use is called calculating confidence intervals. Now we're going to do this on some real data. So you can see I've already loaded this data in here, 48 observations of 4 variables. But actually I'm just going to delete everything in my environment here just so we can see this a little better. And I'm going to load that back in. So this data has 3 variables within it. It's got a continuous variable here, which we'll use in a minute. It's got a binary variable and another binary variable. This is the one we're going to use though. So this variable is about whether the people in the sample have had a cup of coffee today. Now I'm going to transform this into a slightly more usable variable. So it's going to be called coffee rather than this long name here. And it's going to be coded as 1 for yes and 0 for no. We're using if else to do this. So here's our table, and you can see that we've got 31 zeros for not having a cup of coffee and 17 ones for having a cup of coffee. Then the first thing we're going to do then is we're going to calculate the mean of coffee. And of course, the mean of a binary variable is its proportion. So the proportion of people who've had coffee is 0.35, so 35%. The next thing we're going to grab then is the n. Now the n is what we call the length of this sample. And we can run this on the specific variable here. And we're going to get a length of 48. So for 48 observations. Now for a proportion, our standard error is a slightly different calculation. Because a proportion has particular properties. And that's because if we think about our distribution of proportions, well, it has very clear maximum and minimum values. So our minimum value is 0% and our maximum is 100%. Now 35% then is our estimate from the sample. The question we're going to try and answer is, if this is the proportion in our sample, what is the plausible range of values in the larger population that we haven't observed? Now, to do this then, firstly, we're going to calculate the standard error, just like we did before, but this time the formula is p, so 0.35, multiplied by 1 minus p. We then divide that, excuse me, by n, and we take the square root. So in this case then, our formula would be that we would take 0.35 multiplied by 1 minus 0.35 divided by 48, and then we take the square root of the whole thing. let's look at what the answer to that is. Here's our standard error. And it turns out to be 0.0690. Now, the next part of this, though, means that what we want to do is calculate particular points on the curve based on an area under the curve. And to do that, we use QNorm. So let's go back to our graph. So what we're doing is we want two values. And let's call these x1 and x2. And what we want is the area under this part of the curve to represent 95% of possible values. So how do we do this? Well, what we do is we calculate the area under the graph actually for 97.5%. Because if we think about this, what we need is this area and this area to each be 2.5% of our distribution. And what we do to get the x values is just multiply the number that we get from this. So if we want to see what number we get from this, we can just run this on its own. So QNorm of 0.975, we get about 1.96. And we multiply that by our standard error. And what this gives us is what we call the error-bound proportion, which in this case is 0.13. Now, all we have to do then is we have to take our proportion and subtract the error-bound proportion and add the error-bound proportion. So in other words, we just take this 3.75 and we add the EBP in this direction and we subtract the EBP in this direction. So let's find out what those are. So let's calculate P minus the EBP and P plus the EBP. We're going to save that as confidence intervals, 95, and run it. Now what we get is then, this is 21% here, 0.218, and 49% here. So in other words, then our values for x1 and x2 is 22%, 22%, and 49%. So what we can say is then, with 95% confidence, our true population value is between 22% and 49%. But our central estimate is 35%. Now we might say, why 95%? And actually we'll come back to this later. But what we're first going to do is we're going to look at how we do this, not with a proportion, but with a mean. Because if we have continuous data, we can't calculate a proportion, but we can calculate a mean. And in fact, the logic is very, very similar. It just uses a slightly different calculation for the standard error. And instead of using the normal distribution, we have to use, as we did up here, the t-distribution. So this has some language in here about null and alternative hypotheses. You can ignore this in this script because we're going to go over this when we look at t-tests. Here, we're just going to look at confidence intervals. So this is a continuous variable, and it measures how long people could hold their arms out at 90 degrees. But it could measure anything. Now I'm going to transform this into a slightly shorter version of the data. We're going to call this arms. Shorter variable name, I should say. And I need three things to calculate this. I need my x bar, so the mean of how long people could hold their arms up in the air. I need the standard deviation, and I need the length. And actually, just so we can see this, I'm actually going to get rid of this. Load my data back in. There we go. So we've got a nice, clean environment. Okay, so let's look at these. So we've got our x bar, the mean of arms, our s, the standard deviation of arms, and our n, the length. So we have an n of 48, just the same as before. Our x bar is 4.64 minutes, and our s is 2.47 minutes. So let's put that into our distribution. So in this case, then, we've got we have 4 point, I've forgotten the value already, so 4.64. So 4.64. Our standard deviation is 2.47. We're going to still work with 95% confidence, and we're looking for this x value and this x value. And of course, we don't know that our lower and upper bounds have any particular value because this isn't a proportion. Now, our standard error calculation is the same one we used before. So it's the standard deviation divided by the square root of n. So in other words, in this case, our calculation would be that our standard deviation is 2.47 divided by the square root of 48. So what's our standard error? Well, it's, in this case, 0.35, probably 36. Now what we do then is we just plug this into the t-distribution. So this time we're going to use qt, because just like qnorm, as we saw up here, qnorm, qt returns the area under a standard t-distribution. We also, just like we did before, have to put in the degrees of freedom. And again, this is just n minus 1, so 47 here. So let's look at what number this generates. So the number this generates is just a little over 2. And we multiply that by SE. So in other words, what we've got here is a calculation for our error-bound mean, this time, not error-bound proportion. of 2.011 multiplied by our SE 0.35, or say 3.7. And let's look at the EBM. So our EBM is 0.717. This number here. And then our procedure is exactly the same. So we take our EBM and subtract it from X bar, and our EBM and add it to X bar. So we're adding, in this case, 0.71. So 3.92 and 3.36. So again, if we look at this graphically, we've got plus 0.71 and we're subtracting 0.71. And so our X values here are 3.9, and we'll call that 5.4. So let's go for this. 3.9, and forgot what this is. Let's go back to this. 5.36. So just like with our previous example, we can say that our estimate, our X bar, which we would express like this, is 4.64 minutes. Our highest value with 95% confidence is 5.36, and our lowest value is 3.9. Now, we might say, why use 95% here? Because surely higher levels of confidence are better. But let's look back at this and see what happens if we do change that. Now, this would be 99% confidence. So 0.995, because we have to split this between both parts of the distribution. Now, if I run this and run this again, what we can see is those confidence intervals get a bit wider. So now we've got 3.6 and 5.6. So if we increase the confidence, then we also increase the spread of our values. So we might be more confident in the answer. So 99% is only 1 in 100 as an error versus 1 in 20. But it also means we get less useful and less precise information about the expected range. Now, the only way we can change this, really, the only way we can get out of this this trap of higher confidence means a broader spread of values, is actually by changing the n. Because you might notice that n is always on the denominator of this standard error calculation. So we're always dividing by some product of n. Here, n is on the denominator, and of course here too. So that means that a higher n will always lead to a lower standard error. A lower standard error will lead to a lower error-bound mean or proportion. And that means ultimately narrower margins. So even though this is still 95%, we will get values for x and x2 which are closer in. And just to briefly look at what that looks like, well, we could just artificially change the n. So let's change this. It was originally 48. If we change it to 100 and run this again, we can see those are getting closer in again. And indeed, the sweet spot here is usually around 1000. So if I run this with an n of 1000, we're getting some pretty narrow ranges here. So our original estimate was about 4.6, and now our confidence intervals are between 4.4 and 4.8. If we keep going though, remember these square roots. So because it's the square root of n, over a certain point, our accuracy doesn't increase by nearly as much. So we've got some narrower margins here, but the degree to which it narrows decreases as we increase the n. And this is the reason why when we look at, for example, polling data in politics, that usually the standard number of people interviewed is about 1,000. It provides a good trade-off between decreasing our confidence intervals down to around plus or minus 3 percentage points without having to increase this too much. Because of course, if we increase this to 2,000 and we're polling people, that's twice the cost. It takes pretty much twice as much money to spend the time to interview 2,000 people as 1,000 people. But the amount to which this increases our precision is about the same for 1 or 2,000. So this basic law then of how we calculate confidence intervals kind of determines the entire reason why polling usually uses 1,000 people. It's the most roughly efficient number to get as much precision as possible without wasting time and money on increasing the n too much. So this logic then, this idea of areas under curves, and if you go back and look at Chris's lecture, you'll see how the area under these curves is related to something called the central limit theorem. An important thing to note here is that this is not a distribution of real data. This is a distribution of probability drawn from the known properties of probability distributions that we get from the central limit theorem. And you can go and look back at Chris's lecture on this to see how that works. But it means that we can always calculate, if we have a sample mean and we assume that this probability distribution exists, which we have good reason to from the central limit theorem, that we can always generate either confidence intervals, Rx1 and x2, or we can say, what is the p-value if we say started with a value like x2 here? What is the probability that we would come to exactly this value? Now, again, some of the maths might be, if not difficult to follow in a calculational sense, maybe difficult to follow conceptually. But remember that t-test here is going to do this all for us when we get to the next stage. So this is really just a script to show you what's going on under the hood of this function and what the kind of numbers that it's going to spit out, like p-values and confidence intervals, really mean and how they're calculated. So in the next couple of labs and run-throughs, we're going to look at these functions like t-test, and hopefully from this, you'll get a better understanding of exactly what the outputs from this function mean.